Have you ever felt lost trying to find the right design rainfall data for your hydrology projects? What if I told you there is a free world-class tool where you can access the data you need with just a few clicks? Welcome to ARR Data Hub, an invaluable resource not just for engineers in Australia, but also for students, researchers, and professionals around the globe. In this tutorial, I will show you how to select a site, download the data you need, and make sense of key parameters like rainfall IFDs, areal reduction factors, rainfall losses, pre-burst data, and climate change factors. Let's dive in and unlock the power of this platform. Hi, welcome to Water Edu Hub. I'm Amin Tali, and if you are passionate about water, climate, and engineering solutions, this is the channel for you. Well, let's start the process of downloading and interpreting the ARR Data Hub hydrological data in a step-by-step manner. Generally, the information that we are going to discuss today from the Data Hub are going to be used for finding the design rainfall, which is the first step of any hydrological design work, for example, for drainage assets designs and so on. The data available here are free, so anyone can access that, and I think it is also useful for any kind of research studies that perhaps need to play with the design rainfall. Okay, so let's go through. If we look at the basically the website, you can just simply Google ARR Data Hub, and generally that is what is going to appear, and that's the environment that we are expecting to see. So let's do that and enter the portal and choose a site to find the data and download and discuss. So I just typed ARR Data Hub. I enter. This is the basically website, ARR Data Hub home. I click on it. That brings me to the environment that I showed you. This map is interactive, so basically you can just simply navigate on it and choose any desired location. By default, it is located on Sydney in New South Wales. So imagine that similar to the previous tutorial that we had on climate change, I'm now moving this to somewhere in Melbourne. So I zoom in. I want to go somewhere in the southeast Melbourne. Let me zoom in a bit more, something like this one, for example. And once you are fine or happy with the location, or in case if you have the coordinates of your site, you can just enter here. If not, just find it on the map, and then you need to click on the submit. But before that, make sure that you are choosing your desired variables. I personally prefer to click on select all to make sure that I'm not losing anything important. So I click on submit, and basically for this specific site that I've chosen, the information appears. So we are going to go through all the information provided here, but I'm not going to follow the order as it is shown on the screen. In order to have a better flow or the connection between the parameters. So I play around, but I will cover all of them. So the first thing that I'm going to start is going to be rainfall. So if I scroll down, there is this one, BOM IFDs. There is a link for me to click on, and that will bring me to the website of BOM, the Bureau of Meteorology of Australia, to just get access to the IFD data for my specific site. The rainfall IFD basically in the website the BOM website comes in three categories: very frequent events, frequent and infrequent events, and rare events. So it's good to know that for the very frequent one, we are generally using exceedance per year. It's the number of times and even is likely to occur or be exceeded within any given year. And for the frequent, infrequent, and the rare events, we generally use annual exceedance probability, or AEP. And that one is the likelihood or probability of an event occurring or being exceeded within any given year, and generally comes in percentage. Example of that, the very famous event that generally we use for most of the design purposes is the 1% AEP, or 1 in 100. So now I click on this link, and that will bring me here into the BOM website. So the three types of event that I mentioned are presented here: very frequent, frequent and infrequent, and rare. And by default, it is in the middle one. You can play around with it and change it. But before that, let's go through the information provided here. So basically, the IFD information comes in the table form. So you see in the rows the rainfall durations from 1 minute all the way to 168 hours are provided, and the columns are different AEPs from 63.2% all the way to 1%. These are the common frequent and infrequent events. You can click on chart and see the same information in terms of a diagram, but generally most of the time we prefer to play with the table because of the application in the modeling that we needed to provide it in a kind of CSV or Excel based type of table. Another point is that here you can see that the unit is in mm. That means that the numbers you see in these tables are the rainfall depths, but you have the option to change it to mm per hour, and that will change it to rainfall intensity. Again, most of the time we prefer rainfall depths. Most of the hydrological models prefer the rainfall depth values. Okay, now play with this design rainfall frequencies. If I click on very frequent, click on update, so the table will be updated, and you can see that now the frequency terms changes from AEP to EY, and these are the typical type of frequencies we are interested in. Similarly, if I click on rare and update, I will get the rare events. Start from 1 in 100, go all the way to 1 in 2000. So this is also again the probability that is shown in this form, and the numbers are based on that. So let me go back to the common one that generally we use most of the time in the designs. You have the options of exporting this information in different forms. This one in the right will provide you the PNG file. The one in the middle, download all design rainfalls, meaning that frequent, very frequent, frequent, and rare events come together as one file. And you have the option of downloading only the one that is shown on the screen. So let's say I'm interested only in what is shown here. So I click on download, and this one, it's a depth CSV file which is downloaded, and I'm now going to open it up and show it to you how it looked like. The name of the file has the coordinates also printed in it, so it's good actually. And also you see the IFDs mentioned. So for example, if you go for very frequent or the rare, here the name is also going to be different. So these are the kind of conventions of naming here to make sure that you are having the right information. So I click on it. It's a CSV file. You can see the location, the information, everything is provided. And then you see the durations in minute, in hour, and of course the AEPs, and the values inside are the depths in mm based on what I chose last time. Now let's go back to the Data Hub. So the next parameter that I want to discuss is the Areal Reduction Factor parameters. Here, two formulas are presented. No details are provided. That's why I need to elaborate a bit more on this one. But first, let's go through the two formulas. The first one is for the long duration events, and the second one is for the short duration events. For the long duration, there are some parameters shown as A, B, C, all the way to I, and they are region-based type of parameters. So in our case, for the southern temperate part of the Australia, These are the values that are presented by the Data Hub. So now I need to explain what is ARF and how we need to calculate these ARF parameter based on these long formulas. So let's do that. So ARF is basically a hydrological coefficient that we use in our design rainfall to account for the fact that our storm rainfall intensity is not uniform across a large area or a large catchment. Most of the time in hydrological analysis, we have this idealization of saying that, okay, rainfall can be assumed as a kind of uniform, with uniform intensity all over the catchment. But when the catchment is large, that assumption is not going to be that correct. And because of that, we need to have an adjustment. So the rainfall values or the records that we have as a point data need to be adjusted by this areal reduction factor. So how it works? Areal reduction factor generally is a function of three parameters. Catchment area, which comes in square kilometer. Rainfall duration comes in minute. And frequency, that is like AEP, comes in fraction. So for example, if your AEP is 1%, you need to put it in the formula as 0.01. And the information that I present here comes from ARR Guidelines, Book 2, Section 4.3. So how it works is that if your catchment is very small, less than 1 square kilometer, your ARF is 1. In other words, you still assume it that rainfall intensity is uniform across the catchment. Because it is a small catchment, it makes sense. But if your catchment gets larger, between 1 to 30,000 square kilometer, then in that case, we need to use these two formulas that are shown in order to estimate the ARF, or that reduction factor. So as it comes from its name, the reduction factor is a number between 0 to 1. And that's why we need to have a formula to just estimate it for us. There is an exception. If the rainfall duration is smaller or equal to 12 hours, then the formulas are not useful. We cannot use them basically. Similarly, if the catchment is very large, larger than 30,000 square kilometer, then again the formulas cannot be used. There are some recommendations in the guidelines for using like frequency analysis in order to get kind of specific information about that unique catchment that we are dealing with. So in other words, those generalized formulas cannot be used in that case. So the two formulas that I showed you earlier are provided here. The one which was on top last time is the second one here now, for the long duration event. And as you can see, there are parameters A, B, C all the way to I in that one. And as I mentioned earlier, they are coming by the Data Hub depending on the location that you have chosen for your site. Equation 1 for the short duration only needs area, duration, and AEP. So it doesn't matter which region, and you can get the value by this formula. It's good to know that when we say short duration, we are targeting events shorter than 12 hours. But for the cases that events are between 12 to 24, we will have an interpretation process that needs this equation 1 again. So we will come back to it very soon. Equation 2 generally useful for events between 24 hours to 160 hours, which is equivalent to 7 days. That's, I think, the most that we generally deal with in ARR guideline, the longest event that we are generally deal with. Okay, so another point is that in both formulas 1 and 2, the area of the catchment should be equal to or larger than 10 square kilometer. And if not, then we need to do a kind of additional process for that I'm going to explain. So the required interpolations in this process are related to two parts. Number one is that if the duration falls between 12 to 24, then we need to have equation 3 for interpolation. How it works is very simple. You just enter 12 hour into equation 1, which is the short duration formula, to get the ARF of that 12 hour. and then you put 24-hour, which is the lowest value for the long duration, in equation 2, and you get your ARF of 24-hour, and then you bring it in this formula. So ARF 24, ARF 12 sits in this bracket, and then the actual duration that you have between 12 and 24. Let's say, for example, if your duration is 18 hours, you put 18 times 60, change it to minute, put it here, and by this formula, you can simply get your interpolated ARF for that specific duration that you have in mind. Similarly, if the area is between 1 and 10, again, you need to do the interpolation. And for that one, we have equation number 4. How it works is that you just get your ARF by just considering area as 10 in equation 1 and 2, whatever your duration is. And then you bring it into equation 4 with the actual area of your catchment. For example, if it is 6, 7, 5, whatever between 1 and 10, you just enter it as A. That's get a power of 0.4. And this formula will interpolate, or I would call it adjustment for the area. So you get your ARF for that specific area. Things can get a bit complicated if both these scenarios happen at the same time. So that's the case that I call it complex case or double interpolation case. That imagine your duration is between 12 and 24 and your area is also between 1 and 10. So it means that you need to do like 2 rounds of interpolation. So how it works is based on 4 steps. Step number 1, you just assume your area is 10 for now, and then you consider your duration as 12 hour or 720 minutes. Use equation 1, get ARF out of it. Step 2, again, consider your area is 10, just assume, and then put the duration 24 hour. Use equation 2 this time, the long duration formula, and you get another ARF. Then you use equation 3 using the 2 numbers that you found in step 1 and 2 in order to get an interpolated ARF for your desired duration, whatever it is. So I call it D minute, whatever it is. And then this number that I've got, which is found based on area of 10, needs to be adjusted for our actual area. So that's the time that basically equation 4 comes in. And I use the number that I found from step 3. I also use the actual area, put it in equation 4 that I showed you earlier, and you will get your adjusted areal reduction factor for that specific duration and that specific area. Now coming back to the portal, the next parameter that we are dealing with is storm losses. As you can see, for the coordinates that we have shown or selected, 2 values, the storm initial loss of 27 mm and a storm continuing loss of 4.4 mm per hour are provided. There are some notes here that I'm going to explain in detail. So in general, rainfall initial loss is related to the basically the information of the catchment or the data of the catchment before the rainfall even happens. So that's what we call the antecedent moisture condition. So for example, if the rainfall event happens after a couple of days of no rain, then the soil will be quite dry or the soil moisture will be very low. And that's why when a rainfall happens, basically a big portion of that at the beginning is going to be lost as initial loss. So that's what we call as initial loss. So as you can see, it relates to the antecedent moisture condition. Also factors, for example, could be related to how much is the vegetation on that side and so on. So these are the parameters that could affect the IL. The next one, which is the continuing loss, generally is related to the kind of infiltration rate that happens after that initial loss is already satisfied. So basically, it's a kind of constant rate of infiltration that can exist in the catchment. And of course, that one depends on the land use mainly and also soil type. So This is a parameter that we generally use in mm per hour because that relates to infiltration rate. So Data Hub provides that information, but we need to be careful. One of those notes that I mentioned, I'm going to explain later, is this one, that the IL provided here is the storm loss, not the burst loss. So before you bring it into your modeling work or design work, this needs to be adjusted. And I have a reason for that, because if I don't do it, basically my IL is overestimated, and that can create an underestimated runoff, which is not good. So how do we adjust that? We deduct it from the pre-burst. So the pre-burst is basically is the initial part of the rain that we assume. So we can explain it in this way. The pre-burst is basically kind of a small volume of rain that we can assume at the very earliest stage of the main burst of that event, and that can satisfy part of the storm initial loss. So this adjustment make the initial loss a bit more realistic, and or for us perhaps more conservative when we want to go to the next stage and do the runoff estimation based on this rainfall and also the available losses. Coming back here, the burst values are shown here, the median burst depth and the ratios, and then if you scroll down you can see the 10% burst, 20% and 75% and finally 90%. The common one that we generally use is the median one. And of course, in certain states of Australia, there may be some prescribed advice for adopting other values. For example, it is common in Victoria to say that if you're using the initial losses from the Data Hub, which are basically for the rural areas, and there could be like larger than what are actually in most of the cases, you may need to go for the 75% pre-burst values. But yeah, in this case, let's assume that we are working with the median values. So the numbers that are provided here are based on duration. You can see that the durations start from 60 minutes. So we don't have the pre-burst depth for short duration events. These start from 60. And then the columns are the AEP in percentage, 50, 20, all the way to 1%. The numbers in the table, the numbers that are shown are basically the depth of the pre-burst, and the one in the bracket are the ratios compared to the depth of the rain. So for example, if we go to the IFD, that table that we had, let's say for 90 minutes, if I go for 1%, so I will come here, 90 minutes is basically 1.5 hours, and I'm expecting to have the rainfall depth of 48.8. So when I come back here, by right, 0.042 is the ratio, should be multiplied to that number to give me 2. So let's give it a try to see whether the number that is appearing here is what I say is based on that calculation or not. So this is the way that basically these values are generated. So the rainfall depth we got was 48.8 for the 1% AP 90 minutes. And then the pre-burst was shown as 0.042, the ratio for 1% AP 90 minutes, and of course the median value. If I multiply these two, I will get 2.05 mm, which is rounded to 2 mm. And that's exactly the number that we saw in that portal. So basically this 2 mm that I'm showing here is exactly what I calculated. So knowing this information now, coming back to the IL, the initial loss, we should be now able to adjust our initial loss from the storm value into the burst value. I'm going to have the same example. So imagine I have the 90 minutes even for the 1% AEP. I got the pre-burst, and now I want to go back and adjust my initial loss. I remember it that basically my initial loss was 25 mm, and now I'm going to use that one. So the initial loss 25, the pre-burst 2 mm. We follow the initial loss of burst is equal to initial loss of a storm minus the pre-burst value, and that give me 23 mm. There is a discussion on this one also, if you want to really dig into the details, is that the initial loss value that we get from the data hub is based on the median value, and then our pre-burst also is a median value, but that doesn't mean that the deduction of these two is giving me the median value of the initial loss of the burst. So there are some basically discussions around it, that by right, if we want to have the more realistic number for this initial loss of burst, we need to do it perhaps for like different combinations of IL and pre-burst, have the distribution of the data points, and then get the median from that. Studies have shown that if we do so, we will get slightly smaller value. So basically this 23 that I've got here most probably is a bit overestimated just by simply deducting these two values from each other. The next parameter that we want to discuss is the temporal patterns. So here you can see that we have like two sort of information: temporal patterns of something we have to download, and also the areal temporal patterns to download. So the temporal patterns are basically a set of percentages that we provide in order to describe how rainfall is going to be distributed over our storm duration. Ideally, I mean, in most of like textbooks, when we want to deal with the rainfall events, we may assume them as a kind of constant uniform rain, but in reality that never happens. So the rainfall always has a temporal pattern, so they may follow a kind of bell-shaped diagram most of the time, and they can be front-loaded or back-loaded or center-loaded. So that distribution of rainfall over the duration is something that is very important, because that impacts the runoff peak in our catchment, or in other words, also the catchment response is somehow related to these temporal patterns. So the TPs, or the temporal patterns, generally depend on catchment region. So it means that when you go to the data hub, depending on the location that you choose, these temporal patterns will be different, because they are coming from some historical bursts that have been used in order to generate these TPs for us. Rainfall duration matters. So there is a range of rainfall duration in that. So depending on which one you're interested in, the TPs will be different. And of course the AEPs, because we are expecting different trends for very frequent, and rare events. So that's what we are going to explore. So now let's go and download those two and go through the CSV files that are provided to us. Well, after clicking on these two zip files, basically what appears is something like this. For the temporal patterns, you get SS mainland zip file, and for the other one, the areal temporal pattern, you get areal SS mainland zip. So if you click on them and open them, you will get access to two zip file in two Excel CSV files in each of them. But before that, I may want to explain what is the difference between these two. The areal case is basically when you have a catchment larger than 75 square kilometer, and in that case, we cannot rely on the point temporal patterns. So we need to have a bit more like distributed version over the larger catchment. So basically the guidelines offer a different table of temporal patterns for that you can see. If you go there, you see that the catchment size will be a factor to tell us what is the suitable value to choose. So let's do that. So I first go to the initial one, the mainland one. So this one, you see two files, increments and all stats. The one that we generally play with is the increments. The other one is just a backup information if you are interested to go through the details of that. So if I open the increments, you will see that basically for each rainfall duration, start from 10, we have the increments. For example, this one, the time steps of 5 minutes are used. So basically that means you have like 2 time steps of 5, and the increments are the percentage that we need to multiply to the rainfall depth that we have. Let's say if the rainfall depth for me is 80 mm, I need to put 51.27% of that as the first time step value, and then 48.70% of it in the second one. So you can see that for the 10-minute duration, we have basically temporal patterns for frequent, 10 of them, and then for intermediate, another 10, and then for the rare, another 10. So in total, 30 temporal patterns, 10 for each type of AEPs are provided. And then after finishing that, after the 30, we go to the next duration, which is 15. And of course, because it is 15 minutes, you see that now the distribution has 3 time steps, 3 of the 5 minutes. And it will be the same thing for 20 and then 25 and so on. So this table basically provides you that temporal patterns that you want. And of course, if you are interested to know what is the detail of that, here you can see that basically the information behind these temporal patterns, what are the actual bursts that are chosen in order to create these temporal patterns for us, are presented here. So they are the real events basically. So you can just simply follow the codes that was mentioned in the other file and then come back here, find the code that you are interested in and see what is the actual AEP, what is the actual depth of rain and so on. So the real information is available here just for our info. What about the other one? If I go to the aerial case, so you can see that again I have 2. I go to the increments only this round. What will be the difference here for us is a new column that is added related to area, as I mentioned earlier. So this one is basically for catchments larger than 75 square kilometer. So that's why you can see that now we have temporal patterns for different durations. For example, it starts from 720 minutes. And for that one, you see that we have it for 100 square kilometer area, 200, and then 500, and so on. So for each of the areas, you have 10 temporal patterns. And of course, it will go all the way down for very large catchments of 40,000. That's the largest area that you see. And once that one is done, it goes to the next duration, which is 1080 and so on. So it will go all the way down to 7 days long event, or 168 hours. Or if I just scroll down, that will be 10,080 minutes, equivalent to 7 days basically. So that's how it looked like for the temporal patterns basically to play with. The last point is the climate change factors. I have a dedicated video for that, so I'm not going to repeat the informations that are available in that video. So at the end of this video, I will provide a link to that one, so you can go through the details in that video. So in general, if I want to quickly go through, we have this formula from book 1, equation 1.61. We have a climate factor. Rate of change is one important parameter that we get from the guidelines, and the global temperature change delta T is another factor that I need. And then whatever climate parameter you need, like rainfall depth or initial loss or continuing loss, sits behind this bracket, and this climate factor is a multiplier that will be multiplied to the original or baseline value and will get us the projected one. IP is basically the projected value. So the information provided in the data hub give us these climate factors for rainfall, initial losses, and also continuing losses, and also provide us the delta T value. So let's have a quick look at them as well. So the climate factor sits at the bottom of that page after the pre-burst values. it starts with the rainfall factors on the different SSPs, SSP 1, 2, and so on. So you can see each table give us the information based on the duration of the rain and also the projection year that we have in mind from 2030 all the way to 2100. Same for SSP2, SSP3, and then SSP5. I can zoom in a bit. These are the duration specific values. And then we have the loss factors for initial loss. For initial loss, we have SSPs versus year only. Duration doesn't matter. Continuing loss similarly, again for different SSPs and different years. And at the end of the page, you see the delta T values or the temperature changes compared to the baseline year, which is 1961 to 1990. So again, for different SSPs versus the projection year, you will get the delta T value that you need for that formula that I showed earlier. With this, we have covered all the hydrological parameters in Data Hub portal, and we went through the details of each of them. But of course, we can even dive deeper in these topics. I will have a separate video later on temporal patterns and how we basically apply them into our runoff calculation, and also another dedicated video regarding the losses, because there are a lot we can discuss on initial and continuing losses as well, and how to apply them again in our calculations. So that's how you navigate the ARR Data Hub, from choosing your location to downloading and interpreting the design rainfall data. I encourage you to explore it, experiment it with different sites, and see how the parameters apply to your own projects. If you found this tutorial helpful, please make sure to like, subscribe, and share it with those who may benefit from it. And let me know in the comments what topics or tools you would like me to cover next. Thank you for watching. See you in the next one.